In this lesson, we're going to focus on rotations and Cavalieres Principle. So let's go ahead and let's start by looking at some rotations. And number one, they give us a right triangle, and they tell us that we're going to take that right triangle and we're going to rotate it about or around line L in order to form some kind of a three-dimensional solid. So it's important here to slow down and to take a look at what's really going on in this problem. The triangle that we're going to be rotating is this triangle or this right triangle that has legs of length 3 and 4. The line about which we're going to be rotating it is that line L that I just made red in the diagram. So again, it's important to slow down and think about what's really happening. So if I think about what's going on, anybody on this line is going to stay on this line as the triangle turns. But as the triangle begins to turn, it's going to kind of jump up out of the page at us. Then at some point it's going to float back around so that it's lying flat on the page once again. And then it's going to kind of continue onto its journey, but it's going to go back into the screen. So if I think about it, at some point when we flip this triangle over the line, the image is going to be kind of the line, what we get when we reflect that triangle over the line. So we can kind of envision it coming out at us, laying flat on the page, and then continuing its rotation and going back into the screen. But in essence, what we've done is we've created here this kind of cone effect. So sketch and identify the solid formed by the rotation. Well, we've got that cone with the circular base. We've got the vertex up at the top. The height of this cone is going to be 4 inches, and the radius of this cone is going to come right from the dimensions of the original triangle and 3 inches. So the solid that would be formed would be the cone, and the sketch would be that sketch that I just did right there. And now they want us to go ahead and they want us to find the volume of the cone. So like with any other formula, if I'm going to use it, I need to write it down on the paper. Volume is equal to 1/3 times pi times r squared times h. And I'm going to go back to my figure and I'm going to grab the information I need out of the figure. So 1/3 is going to stay 1/3. Pi is going to stay pi. But the radius of my cone here is going to be 3. The height of my cone is going to be 4. And then I'm going to grab my calculator and I'm going to substitute everything that's not a pi or an irrational part of that expression into my graphing calculator. So I want to type in 1/3 times 3 squared times 4. Since it doesn't tell me to round, I'm not going to go ahead and multiply by the pi. So when I multiply together all the rational pieces of that, I end up with 12. So my volume here is 12. I have not yet multiplied by the pi. I still need to take care of the pi. So 12 times pi, and this is going to be measured in cubic inches because the original dimensions of my triangle were in inches. And again, since they don't tell me what to round to, I'm going to leave that as an exact value in terms of pi. If they had told me round that to the nearest integer, then I would have kept going on my calculator and I would have typed in the times pi. But again, since they don't tell me what to round to, I leave that as an exact value. So there's kind of the first part of our lesson, which was on those rotations. The second piece of this has to do with something called Cavalieres Principle. Cavalieres Principle says that anytime you have two figures, or in this case, three figures, three prisms, that have the same height, that's important, the same cross-sectional area at every level, then as a result, they're going to have the same volume. So in the picture above, they've got this square prism whose base has an area of 6. They've got this parallelogram kind of shaped prism with an area of 6. And they've got this triangular prism whose base has an area of 6. So since this cross-sectional area at every level is 6 square centimeters, and they're telling us that they have the same height, Cavaliere's principle says their volumes also must be the same. And I kind of say to myself, this is kind of an obvious principle, I think, in my mind, because if we find volume of a prism by multiplying the area of the base times the height, and they have the same area of the base and the same area of the height, well, then it only makes sense to me that they're going to have the same volume as well. All right, so an example of how you might see this asked on a test is what you're seeing in example 2. It says we've got these two stacks of 23 quarters. One of the stacks forms a cylinder. That would be that first stack right there. But the other stack is kind of haphazardly put together and does not form a cylinder. They want us to use Cavaliere's principle to explain why the volumes of these two stacks are going to be exactly the same. Well, each of the stacks contains exactly the same number of quarters, so the stacks have the same height. That's the first important piece. The second important piece has to do with the area. Well, the area of a cross section is going to be a quarter. And the area of a cross-sectional quarter in the first stack is going to be the same as the area of the cross-sectional quarter in the second stack. So I'm going to say that their cross sections have equal area. And what Cavaliere's principle says that if two figures are equal in height and have equal area at every cross section, the two figures must also have equal volume. So since both stacks have the same height, and same cross-sectional area, and it really is the same cross-sectional area at every level, they must have equal volumes. So that's all I have for you from this video. This one's going to be a short one. But as always, I do want you to take a few minutes and summarize in your own words exactly what are the key ideas and important takeaways from the video, and then see if you can apply what you saw in this video in order to solve the problems on the next page.